So we looked at the linear function, the quadratic function. Let's go another power up, the cubic function. Now, unlike the linear function and the quadratic function, which just has one basic shape, a cubic actually has two different possible shapes. The classic one we think of is y equals x cubed. There it is. It has our one which inflects, which is what we call a point of inflection. And this one's actually known as a horizontal point of inflection, because if you were to draw a tangent at the point where it inflects, it would be horizontal. Anything that has that sort of shape can be factorized to be some constant. Again, that's talking about the, well, for want of a better word, concavity of the cubic, but then x minus a perfect cube. Now, anything that can't come down to be a perfect cube that's been shifted somewhere would have this sort of twisty shape. It still has one point of inflection. There it is at the origin in the one I've drawn. It's not horizontal, however, that particular one. But it also has two turning points. So a cubic would have one of those two shapes. But just like our linear and quadratic, we could recreate any cubic using transformation. So translation, reflection, rotation, dilation. How do we recognize a cubic? Well, once again, we're just looking for the highest powers. So for a cubic, one of them is going to be the power of 1, the other is going to have a highest power of 3. Alright, what about polynomials in general now? I mean, we could keep going up in the powers and the powers. And obviously, the more powers we have, the more possible different shapes we could get. But let's look at these ones, the ones that can be factorized down to be perfect. So some linear function to a power. It's either going to take on this sort of shape, a U shape. I'm not going to call it a parabola because only x squared is the parabola, but it has that U shape. So x to the 4, x to the 6, x to the 8, and so on. Or it will have that inflecting shape like the cubic, x to the 5, x to the 7, and so on. What we should find is, as the power gets bigger, the curve will get flatter at the base. Now I might have slightly exaggerated that a bit with my one on the right hand side here. That's very flat at the base and steeper at the sides. That's what we should see happening to our curve. How do you recognize a polynomial then? Polynomials, we said, all those powers have to be positive integers. Well, or 0 as well, I suppose, accounting for the constant, but they have to be positive integers. And then we have our polynomial. And that highest power becomes the degree of the polynomial. So a quadratic polynomial of degree 2, a cubic polynomial of degree 3, and so on. Let's look at sketching polynomials. What can we tell by looking at the equation? How can we get a sketch? Right, now, it might not necessarily be 100% accurate in some of the features until we look at some calculus and we can really get a great sketch. But alright. Now this one we can work out nice and easily. The y-intercept is always the constant. If I had this particular polynomial and I factorized it, because when it's factorized, I get lots of information. Now the constant number, I don't have to expand the whole thing out, because when I expand out, the only way I'm going to get the constant is multiplying all the constants together. So for this one, I'm getting 1 times minus 1 cubed times 2 squared. It's negative, isn't it? Negative 4. Okay, I'll plot that one in. The x-intercepts are the roots, the solution to the polynomial equaling 0. And for this one, I've got negative 1, positive 1, and negative 2. Now, what happens out of the extremities as x approaches infinity and minus infinity? And what happens is it will behave like the leading term. It's what we say, it dominates. So in any function, when you're looking at things like this, a term that dominates takes over out at infinity and what have you. It's like the other ones don't exist. So when you think about a polynomial, you're raising it to a power. Now, when you're talking about infinity to a certain power, not that you can actually do that, that obviously is going to be a very, very large number. The lower powers become insignificant. I mean, even if you, let's think of a number that's large-ish, 100 for instance. If you were to say 100 cubed, so we've got a cubic, 100 cubed is going to be, what's that? 1 with, how many zeros do we end up with? 9? 9 zeros. So quite a large number. The next term down is 100 squared, which only has 4 zeros. So as far as size goes, that's pretty insignificant compared to the other one. That's the idea of domination. So what's this leading term? X times x cubed times x squared. It will behave like x to the power of 6. That's out of the extremities. What I know from that is, all right, it will start up here, because if I was going to draw x to the power of 6, I would start up there and I would finish over there, just like x to the power of 6. Gives me a little bit more information. The roots themselves behave like the factor. So an even power, when it hits that x-axis, it will act like a parabola. If it was to the power of 4, it would act like the U-shape, flatter at the base, steeper at the sides, and so on. So in our one, I know that over here at -2, it's going to act like a parabola, but adding in the information I know about the graph starting up here, I now know that this curve is going to come down and turn at -2. It's got to do that. The odd ones, likewise. It will behave like that inflecting shape of the cubic or power of 5, whichever. In our one, over at +1, it's going to act like the cubic. I know it finishes up there, so it must come through like that. That's what it ends up being. Now, as I say, detail-wise, where exactly do they turn? At this stage, don't know. It's just a rough sketch. Does it turn before the y-axis or after the y-axis? Again, not 100% sure. Once we start working with calculus, we can identify those points exactly. But for a rough sketch, to get a feel for what the shape of the curve's like, that does the job. By the way, that one is 100% accurate because I actually used a graphing package to draw it, but let's look at circles. Next sort of shape we like, and our basic one, x squared plus y squared equals the radius squared. This is where it's really important that our scale is not only consistent on each individual scale, but we use the same scale for x and y. Because if I didn't, my circle won't look like a circle. It'll look like an ellipse. So these ones we do need. Circles themselves are not functions. It fails the vertical line test. It's a composite of two semicircular functions. Now, how do you recognize it? Well, there it is, x squared plus y squared equals r squared. What am I looking for? Well, now the highest power of the x and the y are now 2. And more importantly, the coefficients of x squared and y squared are the same. Then we've got a circle. If they were not the same, what would we have? And there are actually two correct answers.
Ellipse and hyperbola.
Right. It might be an ellipse, it might be a hyperbola. It's a hyperbola, yeah, if one of those is actually a negative number, you get a hyperbola. But what about those square roots then I talked about there? Functions involving square roots, not just your semicircle. This happens when we rearrange things and the dependent variable is made the subject of the formula. So for instance, let's look at our circle. There it is. It was x squared plus y squared equals the radius squared. If I make y the subject, I end up with, well, maybe this. That's the square root of r squared minus x squared. But of course it might be the negative square root as well. And they're the two possible functions we could get. If it was x equals y squared, and if I made y the subject, I'd get y equals the square root of x. I get half of a parabola. How do you recognize it? Well, if you're ever unsure, square both sides. And then you're going to get the basic shape. You'll see it. So, didn't recognize this. Ooh, what is that shape? Is it a... Oh, square it. Oh, look, it becomes a circle. So it must have been a semicircle I was dealing with there. Over here, y equals root x. Oh, what is it? Not sure. Let's square it. Y squared equals x. Okay, a parabola. Well, half of a parabola. Positive square root, it's going to be the top half. Negative square root, it'll be the bottom half. Mind you, if I had made x the subject, it would not be that. If I made x the subject, then the positive square root would be the right-hand side over with the positives, and the negative square root would be on the left-hand side with the negatives. Okay.